So here we have the exact same system from before, except now with a PI controller. So we'll go ahead and follow the exact same process and find the steady state error of the system in this situation. So again, we define error as the difference between the reference, i.e. the commanded output, and the actual output. R of S in this case is simply 1 over S because we have a unit step input. Y of S we can get an expression for from the closed loop transfer function, which we will call G of S, which has an output of Y of S and an input of R of S. It's a negative feedback structure, so we can use our rule forward over 1 plus loop. Before we do that, however, I want to go ahead and rewrite this so that it has a common denominator of S. This term has a denominator of S. In order to get this term to have a denominator of S, we multiply and divide by S. Now we can combine them, where the numerator of the first term is S times Kp, and the numerator of the second term is simply Ki. So once we've done that, we can see that our forward path includes the PI controller and the plant. So it's equal to 2 times the quantity Kps plus Ki divided by S. That's the numerator of our transfer function. The denominator has the form 1 plus loop, where the loop includes these 3 transfer functions: the controller, the plant, and the sensor. Recognizing that 2 times 5 is 10, we have 10 times the quantity Kps plus Ki divided by S times the quantity S plus 1 times the quantity S plus 5. We then would like to clean this up, get it into the form of a single polynomial divided by a single polynomial. In order to do that, we can multiply through by this denominator. I left off an S plus 1 here in the forward path. So in order to clean this up, we can multiply through by this quantity. When we multiply that through the numerator, the S will cancel, the S plus 1 will cancel. We'll be left with 2 times the quantity Kps plus Ki and S plus 5. When we multiply through the denominator, this quantity will multiply 1. And then when we multiply this term, the quantity will cancel that denominator and we'll just be left with 10 times Kps plus Ki. So this is our closed loop transfer function. We can then use this to substitute in for Y of S, where Y of S is simply the closed loop transfer function times the input R of S. So substituting in, we have R of S minus Y of S, where Y of S again is equal to that whole big transfer function up there. Which is multiplied by R of S. So that gives us our expression for E of S. Previously, we had shown that since our unit step is a finite value, our reference doesn't blow up and our output doesn't blow up, so we don't have an indeterminate form, and we can simply employ this in the final value theorem. Just as an exercise, I'm going to go ahead and attempt to find a common denominator in the case that we had a situation with, for example, a ramp input where the reference and the output were growing unbounded. So I'll take this R of S and I'll factor it out because there's an R of S in each of the 2 terms. And then I want to combine the 2 terms so that they have this common denominator, S times the quantity S plus 1 times the quantity S plus 5 plus 10 times the quantity Kps plus ki. In order to make this first term, which is just a 1 once I factor out the r of s, in order to make this 1 have the denominator I desire, it'll basically have that denominator with an equal numerator. So up here I'll get that exact same expression. And then I will subtract the numerator of this other term, which is already there. When I do that, I'm going to go ahead and distribute these terms across the s plus 5. So I'll end up with a first term that's 2 times kps plus ki times s. And then when I do that for the second term, I'll have 2 times 5. Okay. And so this is the numerator from the first term, which is just equal to 1, and this is the numerator off the second term, where I'm subtracting the entire quantity. And so what you'll notice is this term matches that term, and so when I subtract, they simply cancel each other out. So that's just an example of how we find a common denominator if it's necessary to. Once we have that, we can then go ahead and apply the final value theorem. Where I can use that entire expression for E of s. And so E of s is equal to R of s in this case, where R of s is simply a unit step 1 over s. In the numerator, I have this quantity s times the quantity s plus 1 times the quantity s plus 5, and then it subtracts this other quantity 2 times kps plus ki. And then the denominator is the same as it was. Looking at this limit, we have the s from the final value theorem, the s in the denominator from the unit step reference, they cancel. If I go further, I left off this s, so I'll include that. If we look at that, this function is defined at s equals 0, so we can simply sub in. This term has a 0 multiplying this whole thing, so that will be 0. This term has a 0 multiplying the whole thing, so the whole numerator is 0. And the denominator, this term will go to 0 because we have an s multiplying. This term will go to 0, and we'll be left with 10 times ki in the denominator. So 0 is equal to 10 times ki, which is equal to 0. And so what we've shown is by adding the integral action to our controller, we've been able to make the steady state error go to 0. And interestingly enough, the steady state error goes to 0 no matter what the value of ki. Even for a small value of ki, the steady state error would go to 0. The idea, however, is that if we used a very small value of ki, it would likely take a long time to drive the error to 0. So the ki doesn't affect the final value, but it does affect the rate at which we get there.